right, so we're going to open up with a discussion session, and I know we have a topic of kind of focusing on specific kind of mission concepts, but I want to go back. I know there were a lot of questions that came up with the last panel. So panelists, you don't have to sit up here anymore, but you might get questions directed your way. So make sure to raise your hand if you've got a comment to a question. And yeah, let's go ahead and start with the question in the back. Sorry to make you run, Nick. And Pascal, once Teddy's back in the room, I want to get back to your question as well.
Hi, I'm Christine from JPL, and I was wondering if someone could speak towards the power metrics or power considerations for adding on the payload, specifically from kind of past experience and like things you could do in the future design.
Yeah, thank you. So I can talk a little bit about what we did from Raven, and I do have the numbers in my head from the images we collected. I do not remember the parameters from the point spec and the lift spread. I assume it would be much lower. So we kept it consistent with the mass science helicopter. So per soul, we had 140 MB of data volume and 300 and something, I think 333 watts power. And so we were in the simulation, we were making it very consistent with what was written about the mass helicopter. And yeah, I think that was like one of the reasons why the team decided to use more oblique images, because as you can imagine, if you do survey flights and want to create mosaics and DTMs, you make way more images. So for example, we had 3 survey flights out of a total of 12 souls. And I think they were all on the order of 40 images, which was very important for post operation science interpretations. But the oblique images, you just had a better resource. It was lower on research, lower on the resource site.
And then I'll add, with that helicopter, it was kind of a dream scenario. Like we had a payload of, you'll have to help me, Joanna. We had a payload of, not actually, we simulated a payload of kind of like a landscape style, or like the oblique camera, the survey camera, the close-up kind of Molly-esque camera. We had a libs and then the sampling capability actually. And so obviously a dream scenario right now, but I will say in the paper I wrote comparing the resources, it was never power that was the limiting factor. It was always data volume. So to answer specifically your question about power, power was never really an issue, even with the survey flights, the sampling, what have you. It was always data volume. So in that dream scenario with multiple capabilities and a sampler, which would be amazing, yeah, we did not find that power was an issue. You know, with different devices, who knows? Again, I'm not so much an engineering background person, so I defer to others as well, but that's at least what we found. Paper coming out soon.
So I'll say that with engineering specifically and with similar platforms that are solar powered, where power comes into play is with your overnight survival. And so if you're using a very high power draw instrument, you need a certain amount, right? You charge your batteries during the day, and you need a certain amount of power reserves in order to do your overnight survival, to be warm, things like that. So some of you heard about Ingenuity browning out and powering down during March winters. That was part of that problem. And so if you don't have enough battery, kind of like amount of power available, you can't do very, high power draw. So that's kind of like, from a systems level, that's where that would come into play, where you may not have had a power draw problem and it's like a data rate problem. But from a like mission architecture and systems perspective, that's kind of where your limit would come from.
Just a quick follow-up. What was the ratio of the energy used with CLI versus what you use for flights and like roughly?
So we have 40 watt-hour battery on the baby. We used about 2/3 of that energy to survive all night. And we lose about, depending on the season, depending on when in the 2.5 years, talking about which flight, like flight 9, that's a really long flight. We lost about 20 to 30% SOC rate of charge in that 40. So those are the rough numbers, but 20 to 25 watt-hours at least on a decent overnight survival. And that's only gonna get better with large aircraft. Your service area to volume ratio improves, right? So you don't need to fight as hard, hopefully to stay warm overnight. There's also opportunities to throw in, some several dozen grams of radioactive bead to help stay warm if you really need it for a polar field. But for what we're looking at with Chopper right now, Chopper is the next name from our client's helicopter. At Three Forks, Jezero,
Actually, Teddy, you can hold the mic. Pascal had a question for you that came up earlier and you can answer it.
Hello, yeah, thank you. Could you remind us or update us on the constraints for Mossad helicopters, landing sites? In particular, elevation range, height of hops, duration of hops, and also if you fly higher, for example, the payload is not 3 kilograms, say 1.5.
Sure. So first, let me talk to payload agnostic for some aircraft capabilities, right? If there's one thing I ask you guys to remember coming out of this conference, it's 3 kilos, 3 kilometers, right? That's what we're trying to design the sweet spot for the Chopper from our science helicopter, right? 3 kilometers per sortie, right? And that sortie is going to be a handful of minutes. There's trade-offs where you push higher velocities faster forward, you fly, and generally more efficient as a multi-copter. And 3 to 5 minutes, again, depending on payload, depending on how much wind there is that day. So let's just call it 5 minutes for argument's sake right now. Altitude, that's gonna be restricted to first order by your altimeter. Ingenuity's altimeter crapped out at around 25 meters. We push up to 24, and I think 24 is our highest today. We have already identified a handful of better altimeters that are a few hundred grams heavier that would allow you to go to 100, 200, 300 meters up. That's unlocked. You can assume that you can play around with that. And then the other question that may be pulling in everyone's head is, well, our imaging resolution, what does that do, especially in light of what happened with imaging flight? One of the big things about Flight 72 is that the rover was going northwest, you have to follow, and the landest spring you ever seen. There's a really simple fix for that is you're just spending more than 2 cents on your camera and you have better than VPA resolution, right? So with a future Chopper helicopter, you'll have a better camera that can resolve even the landest frames. You'll have a better altimeter that will allow you to put a few hundred meters and between 3 and 5 minutes of flight time.
Okay, it's a totally different question, but I suspect the reason may be that the mass penalty, but did you ever consider a tactile fan for the propellers?
I'll give my answer and Sarah, if anyone at AV ever recall that. So I wasn't around in the very beginning. I joined JPL leaders, but 2017, the original concept as an instrument proposal for return started in 2013, and Bob Allen started thinking about this in the 90s. I don't believe there was an iteration that looked at ductless fans. Ductless fans give you a lift boost, but you have to pay that mass penalty like you mentioned. So my short answer is I think it was obviated out, or no one ever, seriously considered it, but
Yeah, I also before my time, but I would agree. I don't know that it was ever strongly considered. Engineering is very, very math limited. And so I can't imagine that, you'd be able to gain enough efficiency, for that. But I don't know for sure. I don't think we've actually run that.
All right. I think, did we get to all the questions from before? I see a hand raised in the back. I do want to transition us from the panel where we're just quizzing our experts to, for more group discussion. In particular, we could go on days about concepts, specifically technologies that would help enable them. So instruments, operations, new ways of making measurements, things like that. We want to get those ideas out there, but feel free to continue asking the questions in the back.
Hi, Suniti Karnataka, Louisiana State University. This is a question more for Danny. In the Martian context, synthesizing mineralogy with geochemistry has been one of our major challenges. Regional scale resolution with geochemistry, gamma spectroscopy orbit data, and mineralogy is working at the outdoor scale. Working in between those two can be greatly enhanced if we have a gamma nuclear spectrometer aboard the helicopter design, similar to what we have on Dragonfly. So in terms of the Dragonfly application and adapting that for Martian case, what are the main challenges and benefits you would foresee?
So the question was taking the Dragonfly design, which uses a gamma ray neutron spectrometer to observe the near surface, basically remotely, and then applying that to Mars. Is that the question?
Yeah. One altitude, with the concept, do you think the disparity is currently not in different kind of
Okay, I might need to turn it over to a more Martian person to be able to answer that in terms of if the question is about applying the gamma ray spectrometer to Mars. I don't know if I'm understanding it very well. I'll just say kind of a little bit about what it's doing on Titan. As we understand the chemistry of Titan is that there is deep down a waterized bedrock. Maybe that's exposed to the surface in some places, but it's probably mixed with organics everywhere. And so the way I'm picturing it is it's basically an organic sedimentary bedrock or organic sedimentary layers, almost like, if you go to the Grand Canyon, for example, there's way deep down at the bottom, you have the crystalline basement. You have to go way down there and rely on rivers to carve the surface to get there. And above that are a sequence of layers formed by dune processes or shallow or deep ocean deposits or river deposits, and all of those are sedimentary rocks. Most of them silicate plastic rocks, with some that are limestones. And so the analogy on Titan, as I think of it, is when you have organic plastic sedimentary rocks, right? And that's formed by fluvial erosion and by the oleum processes. And so you would have, from dust up to cobble-sized rocks made of organics. And we don't understand what the exact composition is. And so we need a suite of instruments to help us understand what that's made of. And one thing we can do is drill into the surface beneath us and then draw that up into a mass spectrometer. But having the gamma ray and neutron spectrometer to be able to see compositions right in front of us without having to sample them and wait for that. In addition with imaging to see color and brightness and differences in rounding and angularity and things like that of particles. All of that together is going to operate like a field geologist in person on the surface. So I feel like you could do that anywhere, and that would be a good approach. Where you're using a range of remote sensing plus in situ sampling to understand your environment. If that goes toward answering it, and others might have things to add.
So to bring that back to think about drone technology, what is needed to do that on a drone? I mean, how big are these instruments? Do you need very concise pointing to do it, or can you just like survey a scene?
I think you could survey a scene with the gamma ray neutron
Hold on.
spectrometer. The gamma ray mass spectrometer, I think it's sort of small, although you need the neutrons generated, and so we have to bring our own neutron source on Titan. You can rely on them being generated externally, I think, on Mars, right? And so you don't need to bring that. That's lighter and easier. And then I don't think you need to actually be able to change any pointing. We don't have any pointing changes on Dragonfly. So you just sit and absorb, aim it in the general ground direction always. And so you would, in our case, we operate mostly on the ground. So then you have to decide, you want to also be able to operate in the air, which I think we can also do if we want to, and if we can use the power while we do.
What was just touched on, important consideration role, potential future PIs, and especially for aircraft, it's important to distinguish what are your sciences, landed science versus what is airborne. If it's airborne, what are your point requirements of time and angles, right? If you need your exposure time to be X seconds, and in those X fractions of a second, milliseconds, you need to guarantee that the helicopter doesn't experience dust that rolls you more than X degrees. We're going to think through that and relay that to the engineers so that we can use some statistics on that. We do have a lot. We know what Ingenuity's hover performance is, and we can project that to larger aircraft. But obviously, landed science, super easy. Airborne science with just general engine requirements, old hat, it's been done with Ingenuity now. But if you have some, awesome science payload that needs to hit a single pinhole and not move at all, that's a different ball.
If I could just add something to this, which is, for drone applications, it would be amazing to have a mass spectrometer. But the lightest one that I know is 8 kilograms right now. The TRL-9 mass spectrometer is 30 kilograms, so that makes the drone big. So that's where the challenge is for you, your generation, to shrink it.
Yeah, I think I have a very, hopefully brief comment, what we also learned from Raven. So I do agree. I think it is a very powerful combination to have a camera and then a spectrometer. We have a point spec and the lids on it. And to give you an example, we were flying over the lava flow and found white deposits on it. And so the science operations team decided to land there and do contact science to investigate what these white deposits are. And it turned out it was high-graded silica, specifically opal A, which is known to be one of the materials that preserve biomarkers very, very well. And so I do agree, I think combining camera observations with spectroscopic observation, that's very helpful. It's also combining in-flight observations with contact science while landing.
Thanks. One of the other things to consider is that, like Raven has shown, paired systems like drones working with a rover or a lander can magnify what you can do. There's a real clear challenge to do sample handling with helicopters that's entirely untested and probably ripe for exploration. But if you pair a landed system that can carry, 8 kilogram or 20 kilogram instruments and bring samples to it, you can avoid the challenges associated with how much a helicopter can carry, but benefit from the ability of the helicopter to get to places rovers can't and to touch things rovers can't. And so it's, there's a couple of classes of drones we've been talking about where you carry everything with you or where you carry just the thing you're studying. And then the third way of doing that is to bring the instrument to the sample rather than the other way around. So if you can, land with a suite of 1 kilogram payloads and you can carry only one at a time, you have access for all of your instruments to everything you can reach with the helicopter from that landed spot. And so I think that there's value for the science community in surfacing ideas that are lightweight enough to fly on, distance traveling helicopters up through the chopper class of, 3 to 5 kilograms, but also instruments that would be optionally useful and you don't know which ones you want to use on which rocks or which, identified signals. And so bringing a few instruments and changing them out based on what you find may allow you to magnify the impact of emissions without greatly increasing the cost of that mission, right? You're going to have generalized interfaces. You're going to have to fit the same plugs. And as a necessity, that means that those instruments can't be bespoke to a particular signal you're going to look at. They need to generically interface with the host for them, which tends to drive commonality interfaces and costs down.
Sorry, could you identify yourself? Identify yourself real fast on the mic. Identify yourself.
Oh, sorry, it's Joey Beckman of the Data.
Okay. Hi everyone, I'm Ray Lin Chen. Currently, I'm a postdoc at Cornell University and follow here. I want to draw attention to everyone that there is a spectrometer imaging technique called Raman, because I do a lot of organic characterization in Opal-A by Raman. And I just checked the payloads in Curiosity rover and Perseverance rover. The mass spectrometer payloads, the GCMS suite for analyze organic matter on Mars is 40 kilograms. And for the Raman ones, luckily the Sherlock is only 1.5 kilograms. And yesterday, Kim Farley just released the result that there might be organics on Mars detected by Raman. So I'm thinking about if it's possible to put the Raman spectrometer on helicopter. It can detect both mineralogical and organic matter, and it can do the imaging. So it's very powerful, and it's a kind of a tiny instrument.
What is what we landed, what concept? So you and maybe at the night.
It's not necessary to contact because Perseverance has 2 Raman spectrometer. One supercam is a standoff. It's remotely, it's doing remotely. But supercam is a little bit heavier. It's 5 kilometers because it's a combination instrument combine Raman and the LIPS. If it's Raman only, maybe it's. And Hawaii University, there are many research groups, they just stand off Raman studies. So it can be remotely.
So something that we're doing in right now is we're doing some miniaturization of optical spectrometers, so specifically these ICOS systems. So we don't need to scan a whole bunch of different masses and look at a whole bunch of stuff. You're just a couple of things. So first it's methane. Then you can actually get a package that's, maybe a couple kilograms, maybe you can push it, to be smaller than that. So that's sort of the direction that we're heading. And these actually fly on their own, sort of, to do sort of pipeline analysis and things like that.
Hi, Pascal, in a second. Another question about Mars Science Helicopter. What's the landing accuracy? So for instance, if taking the example was given for Raven, let's say on one flight leg, we identify a target that's, the size of a boulder or something smaller than that, but can you on the subsequent flight actually land over it so that your instrument is right?
Microphone's coming.
2 variables it depends on. One is what environment of Mars we're talking about, and what is the average wind speed and worst case costs in that environment. That's really the driving problem. Is you're coming down, you can't decide your horizontal velocity, grade your position controller, things you take your part, okay, now come down and land, and you're fighting the entire time to hold the position as best you can. At some point, you get to the point where you're gonna stop fighting, and for vehicle safety, you're just gonna go down. And your worst case gusts will define what that error or disturbance is into your disturbance reduction, position control. I'll tell you for SRH, for example, for the simple recovery helicopters, never part of MSR, we were designing for a landing pad. What was the landing pad, like 2 meters?
Position area.
So yeah, thank you, Joe. 45 centimeters is our position area for SRH. So Ingenuity class there. You bump up to chopper now, MSH, your drag that you're presenting to a side wind force is bigger, you're bigger, just in the air, right? But at the same time, you also have a lot more horsepower. So it's difficult for me to give you a number. I would say today, out of thin air, I would be comfortable, saying we could land chopper anywhere on Mars, being widely ignorant to what the polar wind environment is like right now. But we should be able to do it within a couple of years. But trying to get better than that, again, I could be wrong, I won't be having the worst case guts that the poles. But that's the ballpark for the condition.
So that's useful to know, right? Because if you see a target that's of that scale, it's reasonable to divert to go check it out.
Oh, yeah.
It's much smaller than.
It's a low stakes sort of thing too, because, oh, you missed it? Okay, just do a little hop and try to do it again, right? Try that again, maybe in the same stall. You can have that autonomy, design that, based on that, and then for SRH anyway. For reattempts on driving, for example, you can imagine autonomous reattempts for just do a simple pop-up, try and hit the same target again and hope that a wind gust doesn't hit you.
Thank you.
It's always out of thin air.
There we go. Art was saying it's always out of thin air, so you should get t-shirts.
Just along those lines, as Mike is getting moved, I want to point out, unfortunately, soon Joe had to leave because he's in Korea right now. But those going on the tour this afternoon, that laboratory works on that autonomous navigation and safety and everything that is being talked about of how much autonomous work can be done by the helicopter so as to pinpoint landing, safely navigate the air gust, all of that. So that's a great place to ask those questions.
Mark Markowitz from JPL. I think this is for you, Teddy. I'm wondering from science data perspective, like for the next gen chopper class, do you guys have a baseline yet for how much data you can pull on board and how much you be able to transmit?
So we're all, right now, unless the MSR redesign changes things, all future helicopters can have direct orbit comms. It's a huge priority for us. The whole heli team, us, AV, we're all, we know that that's what we need. The easy part, your onboard storage, it's gonna be gigabytes. I mean, 32 gigabytes plus, especially with future aircraft, I'm sure you can all count on 128 gigabytes of flash, no problem. Ingenuity, for example, she's a weather station now, landed vertically. She has 20 years worth of storage that she's gonna be filling up with image data and weather data every single sol until some astronaut goes and grabs it. So for your use cases, you'll have hundreds of gigabytes easy. And if you wanted terabytes with choppers mass margins, you could throw SSDs on them, maximum capacity. The tricky part is your uplink data volume, right? There's two questions I mentioned you're interested in. One is what are you capable of, and then what's needed. Both of those depend on what orbiter fleet exists by the time your mission scales, right? The existing orbiters are aging, right? And there's going to be orbiters slated to go with MSR, right? From ESA. And that one has multiple passes per sol. For SRH, we were planning on using that for signal data volumes, which was in the kilobytes, because we weren't trying to send images back down to Earth. We're at the conference level now where we can plan flights at speed flights without even looking at planning sites. If you pre-map it, we know where. For future, the second part of the question is what are you capable of? For direct orbit comms on a helicopter, that's still being designed, and per sol in the number of passes that would be overhead enough to get a good amount of data up is a heavy factor in. And I think we're doing that local workshop, I'll go call my telecom leader, and maybe in an hour, I'll give you a hard number on what we think we should be able to accomplish there. But it would be a respectable amount of data compared to what you're all used to, for instance. Yeah.
Hold on, use a talking stick.
So the point was, with Perseverance, there's two passes, capturing day passing, and I'm imagining the future, the MSR, ERO orbiter that goes multiple, I think it's like 5 or 6 passes per sol. And whatever other future orbiters are going to be sending, you know, hopefully there's more passes. So with each one of those overhead passes, we're going to be dumping data up to the orbiters. So it'll be a lot of data. Exactly, there's another thing. Making your point.
Porque el árbol comienza. So EO will be there until the samples are shot back and captured, and then we'll bring back to Earth. It will be a few.
So that's an open question in general for future aircraft. There needs to be some local asset to make direct to work. Direct to Earth is much harder and probably heavier. And we'd rather not waste the mass doing that and hope that there's some other local facility of.
Okay, I have a question for, it might even be for Serena in part, going back to what was presented in the beginning about, the kind of ability to have the, system tell us when to take measurements. That was really interesting to me, and I was wondering if folks can speak more about that, and, both from a scientific standpoint, what that would mean, like, are we talking about saltation? Okay, we want to observe grains moving, so wind sensors, or are we talking about some sort of imaging? And then maybe we can talk about how that would, like, the implications of that with like engineering, because for instance, when you had responded earlier about the need to like have 2/3 power versus 30% at night to survive. I would love to hear more about those kind of background observations that might happen, or whether or not those would happen at discrete intervals, and yeah, more about that. And whoever can answer.
Mark, do you want the microphone set up to you? I can start the answer. Okay, so Mark and I have been working on this. The example that was brought up, this is not using a drone, but this is landed science. Particular case study that we're doing is looking at dust doubles. So right now, Perseverance, right, has a pressure sensor, and so that is the information that is used to identify dust doubles, and that's a fairly low power, low data volume instrument. So you monitor this time series, it's just looking at the pressure deviations. If you could use that to tell your cameras and your dust sensors and your wind sensors to turn on, because those are the high powered, high data volume instruments. Right now, my understanding, and Brian can correct me, I think Perseverance has caught like 2 dust devils on camera, just kind of serendipitously as it passed. But if you could turn it on and tell it when those dust devils are coming, you can get all of that information each time with a very strategic use of power and data volume. So that's one sort of application. That's not a drone application, but context science. You could land your drone and do that sort of thing. But the other one that Brian's been working on, right, is using the drone itself is already responding to the environment. It has to know what the wind gusts are in order for it to navigate. And so you do have, I think, the capability for in-flight processing of that type. The processes are already there. It's just figuring out the application and routing it to the instrument. But what you generally need with these is some sort of low power, low data volume instrument that is on monitoring, and use that as the trigger to tell other things to turn on. Another area where you might want to use that is maybe detecting interesting targets while in flight, right? And diverting or finding a good landing site, right? Also for safety reasons and being able to autonomously. Is that what you had in mind? Yeah, good.
Curious to hear more about it. That sounds awesome.
Yeah, so Brian or Mark, do you have anything you want to add to that?
Yeah, this is a really exciting area, and I think so. Goddard is working on it, we're working on it at JPL, but it's kind of very broadly thinking, we can onboard, when you're padding flights or you're driving, think about autonomous driving, that's like taking the camera or other sensor data, like engineering sensors, right? This is like take the same idea, but now let's do that for the science data. And so what can you do either to prioritize data on board? So take as many instruments as possible, allow it to only send back a couple percent or like 30%. I adapt within the environment. So I'm somehow responding to science data and changing my flight paths or doing things that improve the scientific interface rather than just like rescheduling it.
Remember to identify yourself.
Yes, Manuel de la Torre, JPL, also Perseverance Atmospheric Station. We have seen, as Brian pointed out, quite a few more than this, a couple. The challenge is in terms of identifying, because we do think about even already for REX. So we thought of an event mode that would be triggered once the atmospheric station detect an interesting event. We do not have predictors for dust levels as of now. That's the challenge thing. And based on the images or based on what? On the pressure sensor? Okay. So yeah, we will talk about that later. They also predict eddies or not all, and that's interesting. They don't always bring dust, but yeah.
We'll do one more question or comment, and then I want to switch to a question that came in online.
Hello, okay. Hi, Carissa Campbell. I just want to expand on the dust level thing with imagery. It is very hard to see even waterized clouds from just imagery and the raw images. And it seems so with dust levels, and I know Mark Lemon has to use imaging techniques based on the main frames. So you need to get the frames first, look at them, and then be like, oh, there's a dust level there. So it's very interesting that the pressure is able to kind of look at it first, but just using imaging techniques is very hard to predict where the dust level is going to be. In some cases, we'll be looking in one direction, not see dust levels, and realize they're behind us because we're not imaging it. Okay? So it's a very unique way that we have to explore how to find these dust levels and just I think we may be needing to rely on the pressure a bit more to be able to pull that out.
All right, thank you for that comment. We're gonna switch to a question that came in online. Roberto, if you want to unmute and just ask your question, I'll give you a moment to do that. Otherwise, I'll read it.
So yeah, well, we have been working on this drone-based GPR. So we have a DJI Matrix 600 with a terrain following system and a 80 megahertz GPR. And on these terrestrial debris covered glaciers, even if though they have slope and boulders and they have a rough surface, we still manage to follow the terrain. We have found that 2, 3, even 5 meters is a safe altitude, and also we get in glacial reflectors. So I was wondering if on low bay debris aprons, for example, that have a relatively lower slope, let's say like 2 or 3 degrees on Mars, you could conduct with the Mars Science helicopter a flight with a constant altitude, and also if that constant altitude can be, for example, less than 10 meters. I was wondering if there are some constraints on power or, for example, the atmosphere or something that would not allow you to first maintain the altitude and also fly very, very low. So that's are my 2 questions.
In terms of the guidance navigation control, yeah, I mean, that's a solved problem. Doing terrain color radar, DoD figured that out dozens of years ago, in the 70s, 60s, right? So we can implement that on a helicopter. There's a sensing modality. You need to make sure you have a sensor for it. that is designed for the worst case, if you want to do like a positional FFT of your terrain, if it's high frequency terrain or low frequency terrain. High frequency terrain, you just have like a mountain show up out of nowhere, you need to look far ahead. It's low frequency terrain, you don't need to look out as far. That's the first part of it. The sensing, again, money in here, or handle that, it's already solved in many instances. On the aerodynamics front, though, you want to make sure that you're covering, I guess, if you're going forward, the ground effect has one effect on you versus if you're hovering in place, ground effect is different. Hovering at 1 meter above the ground with chopper wouldn't make me super excited to do, all the time, like half a meter, this is a big aircraft. Imagine Perseverance hovering, just above the ground. You're gonna get ground effect. There's an efficiency bump, if you're in ground effect, but at the same time, your air is not as clean. Doing a couple meters, 3 meters, 5 meters, I'm sure that would be a perfectly doable thing. We would just need to know that's a requirement and need sensors for rainfall and radar. Or you could do image based if there's enough texture in the brain, totally doable. We're happy to implement it if you like.
Alex Singh from NASA. For meteorology, it'll be really interesting to get some high-speed flights, maybe 500 meters, kilometers. What do you think would be the typical range of winds you could tolerate? Could you fly in 10, 15, 20 meters per second?
Our upper limit right now, those winds are sustained average wind velocities or gusts.
I'll talk about gusts.
Yeah, so when we start talking about 15 to 20 meter per second gusts, that's when things start getting challenging. One of the big concerns are your tip speeds. The tips of your rotor systems are the best moving part, and if they start going transonic, one side of your rotor that is attacking the wind faster than the retreating part of your blade, you now have an imbalanced lift. One side of your rotor is going to momentary stop. And you can experience partial momentary, well, we're going to explore that next year. How much can you experience momentary storms will be okay. But 20 meters per second is eating into your wind gust margin, right? So there's how fast are you moving through the wind, and then on top of that, gusts, and you just need to stack up that margin and figure out for what part of Mars are you flying and how close you get to the speed of sound on the tips of your rotors there. There's other knobs to play with, but as a rule of thumb, I would say 15 meters per second, and above that is starting to get a little easy.
Sorry, there's also this is Joey Beckman for environment. There's also some aerodynamic and flight control challenges. These helicopters are designed to fly at all. They're not designed to climb quickly. And so given flight time constraints, altitude may be simply out of reach for energetic reasons. You can't get up high enough, fast enough. You stay there long enough and take those readings. The other part is that the density profile on Earth and on Mars are substantially different. People here know it much better than I do. But the vehicles so far have been designed to operate in a particular region, particular altitude band, and they will need redesign in order to have a wider altitude band. It hasn't been a requirement so far, but it does drive aircraft design.
I'm sorry, I probably missed this part of the conversation, but I saw in Serena's notes, people were talking about mass spectrometers, and how they're too large for these types of mission profiles. Just wanted to mention that someone at NASA Goddard, Mahmoud Sultana, is designing a really small sensor package to detect atmospheric trace gases, and in theory, with some modifications, you probably can detect evolved gases from a solid sample as well. And she's been testing this in Alaska with P-STAR funding to localize biogenic methane emitted from wetlands in northern Alaska. She's maybe even out there now. So, this is an idea that's been in work and could be applicable for this type of mission profile, looking for trace gases in the atmosphere.
This is David Saber's work.
And who is it that's done?
Mamuda Sultana, I can spell that for Serena and add that to the notes. The mass is at the moment small, this is still like a TRL 3-4 kind of range. You know, so in a certain way now it's under a kilogram, but flight version, it might be more.
Sorry, go ahead, follow on. Yeah. Go ahead, John.
Okay, yeah, just where you said, how many daily slippers work is the other bullet point in that on there, so that's the mapping instrument that she's at, Northern Arizona University.
I'm just gonna interject real fast here and then get to your question. This is part of the role with it. This conversation is going great. We're not following it on the agenda, which is totally fine. Are folks okay with us just running to 11:45? If you need a break, please stand up and take your own break, but otherwise we'll just go to 11:45 with this discussion. Okay, okay.
Hello, I'm Juan Lorenzo from LSU, and my interests deal more with what happens at landing and takeoff. And I was wondering if, for geotechnical characterization purposes, whether there's currently data or with minor, without having to go through a more complicated unit of engineering, could the engineering be slightly modified to maybe characterizing some of the geotechnical properties when taking off or landing, would maybe just improve the acquisition rate a bit, so.
Want to make sure I understand you're asking, could you do a better job of what are you exactly doing? Clearing more sand underneath as we take off? Is that what you would want? Sure. Right, so there's a lot of data mining to do and a lot more analysis to do. This should excite hopefully a lot of you in that we're planning on releasing all of the onboard telemetry, all of the, well, the images are already out, but the onboard state information, multi-flights are going to be released to the TES and the press data that. From that data, you'll be able to back out the aircraft's release state of what was its vertical position, a vertical velocity, horizontal position, horizontal velocity for all 72 takeoffs and landings. So yes, it'll be there for you. In terms of could future helicopters collect that state, that information better, they could log it better because Ingenuity didn't log it before they downsampled the information and wrote a downsample for that. So that's sort of important for future missions. It's good to know. And we could make that flight software optimization to make sure we get the full, 1,000 per accelerometer data.
Yes.
Yeah.
You can reach the guidance.
Yeah, so the control loop internally operates at 500 hertz. And then we downsample that, I think 30 hertz is what we report on this. Don't quote on that second number, right? It's been a couple years, but it's downsampled. So if you want the full rate, let us know and we can implement that. Sure, you could save your focus time for the high rate activity, but I had touched on it for a second. It's whatever we down, I forgot if it's 50 or 30 hertz, so it's 50, okay, so the 50 hertz, again, we're putting a lot there for the PS hopefully in the next months, for just funding and time will hold us up.
Susan Don Banfield at NASA Ames. I just wanted to come back to that event-driven activity, and there was some discussion about saltation sensors. Potentially high resource instruments. They're not. We're building one that runs at a fraction of a watt, and so you could run that continuously, just like your pressure sensor, and react to when grains start hitting your helicopter or your lander or whatever. And
modern wind sensors are also much lower powered than our existing ones on the rotors. We have this fancy sonic anemometer that runs at 20 hertz at about 1.5 watts. And if you throttle it back to 1 hertz, it's 2 or 3 tenths. So these are very feasible, I think, to put on a link platform. Just comment.
And just follow on to that, sorry, Don, I think earlier, I've been talking about the dust sensor as opposed, and the wind sensor as opposed to your saltation one. Microphones, I think, are also kind of a cool device for monitoring the environment.
Hi, Jamie Eisen at York University. I was just wondering if there's any concepts or ideas of copters that could explore depths such as like lava tubes or deep craters or valleys and then.
Joey Beckman, Air Environment. Some of the capabilities are extinct in other systems on Earth, but physics are not prohibitive for the smallest helicopters we're looking at. What we don't know as engineers is probably also what we don't know as scientists about the environment. And so a lot of the work that needs to be done to make that happen is how to move decision-making from on board to the helicopter to react to increasing knowledge as you fly there. Now, what you do about what you are.
Yeah, so thanks, that's a great question. I think moving a little bit towards the interior processing that are currently ongoing on Mars. So I think lava tubes, ground penetrating radar sounder would be, I think, one of the instruments that I would want on drone to find that, as well as like if you're looking for ice patches and the shuttle subsurface, like ground penetrating radar sounder are ideal to get the interface of the different materials. I think a question that I would have, and I don't know if we have a seismologist or magnetometer expert in here. I think in PlanetInsitu24, since we know there's but potentially melt movement in the surface. I think what I was wondering is there like a very simple seismic experiment we can do to constrain where the melt was moving and if there's actually not moving. I don't know if we have an expert in the room.
Well, I'm certainly not an expert. I'm a sedimentologist, but I've been in planetary science summer school all summer working on a series concept. And so I've read a bit about these, and I would wonder if there's nothing we can necessarily have consistently on the helicopter. Like I know there's magnetometers that orbit planets and acquire data about the interior in the magnetic field, but I would wonder if we could deploy something from a helicopter. So that's not answering your question, but it's kind of like expanding your question as well. And I see something that.
So there was a talk yesterday too, actually, who proposed to put a magnetometer on a helicopter. But they were mainly talking about the science and then emphasizing that helicopters might be amazing to answer our questions.
So yes, lava tubes, it's in the Mars Science helicopter sizzle reel animation. If you look at it on YouTube, you know, that's exactly one of the use cases we want to explore is fly down where the rovers can go. The other idea about dropping things, one of the ideas that came out of JPL the last couple of years is this idea of a tube pod. the size of an MSR-72, but as a single lithium battery in there, small cell phone chip, its own solar panel, or maybe just no recharging whatsoever. So you could imagine carpet bombing a lava tube with a, handful of these things. They're about 150 grams, 200 grams a pop, so easily carryable by a chopper class vehicle. And then one last on magnetometers, yeah, that's super exciting. Magnetometer use case for chopper. You'd think with all the magnetics on the thing, it would kill you, but it's AC magnetics, and apparently the science use case is the DC field. So as long as we calibrate out the hard and soft iron in the actual helicopter, hopefully the rotational magnetic field are not a concern.
I'm Carissa Campbell, Vanessa Butter. I am on the Insight team. I don't work very much with seismology, but they had a conference last week about it. And one big problem with the seismometer is just the noise that's really associated with it, even from wind or testicles. And even though they have to put a cover over it, that is still very noise generated. So I'd be a little worried with dropping a seismometer on the ground and then being able to cover it and then worrying about anything else like that. Especially one thing they did bring up was they wish that it was more on bedrock rather than on regolith, and that may have affected it too. So there may be some nasty constraints that even though we want seismometers, I would love one as well. It may be a little bit hectic to try to put that there.
So just a comment about some. Comment about lava tubes. Very exciting prospect, and definitely Teddy and Carolina can build your helicopter to flying. But you have to make a science case, right? If we have one helicopter every 10 years or 15 years, we got to go to a priority spot where there's breakthrough science. So one of the things you could do, write a white paper, make the case. Is it frozen water? Is it maybe higher potential for life to be preserved because of lesser radiation? What is it, right? And then you have to look where these lava tubes are, because are they in accessible places? What is the latitude of these lava tubes? Is there anything around them? So is the lava tube the only place where you do science, or are there some exciting areas around it, right? That allow you to do more science. So these are the kind of things, try to do a white paper, define your science, and that will be definitely under consideration. It's an exciting look at, that appeals to people's imagination.
So, speculation as to I've heard in the past people talk about sending one of these to special regions. And I wonder kind of what is the planetary protection implications when you're hovering 2 meters above a special region, but not touching the special region? What kind of gray area does that put you in that, to make it super clean like Perseverance, I would think that this could kind of blow your budget pretty quickly. Whereas if you're, relatively quote unquote dirty, like something like Insight, you probably can get by with, without that additional cost burden. So, how proximate do you have to be to something special without touching it to, not be touching it?
Teddy.
I can't tell at all to the piece to the question you asked, but I do want to comment on the preparation of the spacecraft. Unlike Perseverance, Ingenuity, for example, most of it's baked, right? A lot of the composites, and if we have something that is separable and small, you can bake the crap out of it, not have to worry about it from a bioburden perspective. We were cleaner than a lot of the other things on Perseverance from a spore count perspective. We had a pretty stellar BP record. The larger aircraft though, right, you're gonna have to deal with that, I imagine, PCL-wise. So if you go with an X-Copter or not Copter, God knows what, 50 years from now, being able to bake out an individual arm, you can do that with the road. There's nothing sensitive on that. Just copper and some magnets. So you could thoroughly bake out and lessen your PP threat. There's still just the other side of the question though, is that it's still okay to hover over a sensitive area. I don't know, not for me to talk to, but I'm saying you can bake the crowd out, it's helicopter, so it'll be okay.
Thanks. So Matt William, Berkeley. To go back, I guess, to the 90-kilometer question, yes. So yeah, even on Insight, you just slap on that 90-kilometer side of on the side of the lander. There's still a lot you can do with the AC signal, like you said, and people are really smart. People are smarter than me to work out how to use the DC signal. And so with the drone, you get multiple points that you basically can do a 4-person network where you can map out how the field changes, the static field changes multiple points, also AC, how the AC field changes. And it's super easy, make really tiny. Jared Espley had a poster where they make that science grade magnetometers up to a few hundred grams, but you can get your cheap cell phone magnetometers. And any of that would be spectacular. The AC signal, which happens to some space physics interactions and if you get the DC signal, then that gives you a whole bunch of geology there. So, personal opinion, everything shows on like this platform side and the outside side of it. There's a lot you can do with the activity.
Been checking how big are magnetometers? I assume they're small. How big are they?
So like the commercial, cell phone ones, like Coach's kind size and even tiny. But I mean, I know that Goddard has been working on, small ones. Or I think Escapade has small magnetometers, but I know that Jared said they're, electronics and everything, 200 grams. I don't remember the size of them, but we have 2 centimeters or so. But I'm surprisingly small. Yeah.
Mark West, JPL, getting into some of the crazy uncle ideas. Maybe this is a question for you, Don. Do you think, so with these drones, we have the ability to generate winds. Is there anything you could do with that to pulse the ground and see how saltation changes or from dust lifting at different locations?
Jamie or Don, you want to go?
Is this on? Yeah, I thought, we talked about doing that with Ingenuity, actually. Yeah, so, yes, you can. There's a little bit of a question though, of whether it's truly representative of a natural, saltation or dust lifting event, because it's pretty contrived for that. And the other thing is, if you want to do it, on your way down, not on your way back up, because you've already screwed up the surface as you came down. So there's some logistics that you want to think about, but yeah, you can do some. You can use the rotors, I guess, as an experiment themselves, and I think Dragonfly's going to do that. Right?
Yeah, policies there, we plan to do that.
Can you confirm that they plan to do that with Dragonfly? Do you have more you want to say? Okay, thanks.
So since we're landing in a dune region, we know that saltation has happened. Does it happen now? That's another question that we can maybe answer even just geomorphology. But one question is, how do the particles behave in a saltation environment? And so we don't have to plan on there being wind curving when we're there. We can just fire up the rotors and watch particles move and see how saltation happens. And that will inform things like density. Then we can also retest density, particle roundness, and other kinds of things like that. Compare the curve with saltation.
There's a hand in the back.
Suniti Karunathalika, Louisiana State University. One of the challenges with chemical maps on Mars has been, so there's a comment, has been the thickness of the dust layers, the tiny grains on Mars, how much they may obscure underlying geochemical signatures when we map out. And that raises the question of how significant are these geochemical maps when you're trying to inform long-term geologic evolution of the planet, like volcanic processes, sedimentological processes. If with the helicopter designs, we could disturb areas with mapping units to see roughly what the thicknesses may be of the fine grains. That could go a long way towards resolving that unknown. If the helicopter designers can think of ways to do that safely, getting rid on this spacecraft, and of stereoscopic imaging, perhaps to get a sense of how much depth excavation happens, what are the saltation and lofting properties associated. That could also address additional questions on dust transport on Mars, as well as atmospheric dust constituents.
Now picturing sending a giant vacuum to Mars.
So I'm not sure if Teddy or Sarah would be better to answer this, but one of the challenges that we often have people say, oh, aren't you worried the helicopter's going to tip in the winds? And the answer is it doesn't matter really what the wind speeds are because the density is so low, the actual forces are terribly low. And so when we're talking about, inducing saltation or kicking out dust to see what's below it, it's important to remember that at these densities, even though these helicopters are moving a large volume of air, they're not moving a lot of air. And so it's hard to move even anything but the lightest particles. I think the initial indications from seeing the clouds on which it lands, right? There's clearly stuff moving, but it's probably not getting beyond the lightest surface level disturbances. That increases as the vehicle size increases potentially, but it doesn't go up by a factor of 10.
Janie, given the answer and Titan is so much denser, is there more concern about kicking up too much stuff?
I think everyone is just starting to think about dust more and more on Titan. I even think we've raised the idea that, well, if there are so many dunes, the entire equatorial region is basically covered in dunes. It's covered 25% of the body and rings the equator. These are large linear dunes like you find in Arabia and northern Africa. And so it's a sort of a different kind of dune form than we're used to in North America. So there's a lot of sand. And in those places, big dust storms get kicked up. You maybe see the images of off the coast of Western Africa, big plumes of dust that get wafted during dust storms there. So, but our observations of dust storms on Titan are not very abundant. We just, number one, we don't have the image resolution to be able to pick that up, and we've got a thick and opaque atmosphere to look through to get to that. So there are some observations that indicate there should be some, but the rest of us also think well, there should be a lot of dust. So what is that going to be like on Titan? How are we going to, what will we see? And I was just thinking about this experiment of using the rotors on purpose to do saltation. Well, is that going to loft a lot of dust that will then just sort of fill the area and take a while to settle? And because the atmosphere is more dense, it's like maybe walking through down quickly. So yeah, I think that's a good consideration.
For you guys, right? We saw 2.5 years saying it everywhere, and we got inside of our electronic box, inside the sapphire window, the camera window, so green flag you see stuff rattling around, like little stamp particles rattling around in the movie. given that you're gonna be energizing a lot more sand particles, what's Dragonfly gonna do for its emitters, lenses, clear, stuff like that?
So you do nothing. So, Pascal was worried about that as well. Yeah, there are no dust covers, there's nothing, no sort of blowers or anything to help clear them off, so. But just the idea is that, well, you know, we're in a desert environment and hopefully, and maybe Ingenuity is a place to look out for that, but I don't think the cameras got covered.
Yes, that part. But it's that part,
Oh, okay,
but still saying that means that part.
I see, I see.
Branding, and then.
So you can start seeing that, which is, I imagine the same thing's happening about 3.5 years. We'll be on the ground most of the time, we'll fly once a month and be on practice.
Hi, Nick Gamer of the University of Oxford. I just have a question about Titan and the kind of dust aerosols that get picked up into the atmosphere with the denser atmosphere. Do we know anything about, have we done any modelling on like the courses of grains that could potentially be, you know, aloft in the atmosphere or pushed up in the atmosphere when Dragonfly actually lifts off the ground? Have we thought about like maybe the size and what that could do? Because that would obviously have implications for the actual propellers themselves, etc. Just like to.
I think we're considering all the particle sizes that could exist, and then, you know, just like a typical dust load for the environment and just what we might expect from that. And again, you know, all we know about the composition is that it's organic, and so we have maybe a density, but we don't necessarily have like that angularity of the particles or anything like that. And the dust size would be different from sort of clay dust that we're used to on the earth, and so how would that behave? Maybe they wouldn't stick together as much, or maybe they'd stick together more. I don't know. I think there's a lot more thinking to do on this topic. So
I'm kind of pivoting to a more general question, and this might be a question that Janie, you're well suited to answer as well. Sorry to put you on the spot. But so I'm more so know science with rovers, so I know we take a NavCam mesh and then look at it, pick science targets, and oh, there's something in the background. Let's drive there instead. And sometimes that can happen if there's ample justification. With drones, I imagine, you know, as you're planning the science, you're looking at orbital images, and you're like, this is the area we want to land. Here are some preliminary. I don't know what stage Dragonfly's at, but like here are some areas we want to fly to. But is there technology / room for that sort of opportunistic investigation when you're on the surface with drones? It doesn't just have to be tight, but I figured I'd ask Janie since you're in the planning stages now. And what would that look like? Especially in the vein of like, you know, for instance, habitability. If you see anything that was particularly robustly, like it could be evidence of something, that was a weird phrase, but there it is. Could you be like, wait, just kidding, let's go over there? Like, what are the limitations with that sort of thing and what are the capabilities? And anyone welcome to answer, but I figured I'd put you on the spot.
I can start with Dragonfly, sure. And just to round out again this discussion, I heard from Jason Barnes, who's the deputy PI, because I asked him about this, and he said, yeah, we're flying during the dry season, there's a dust repellent coating, and then he's also worried about adding motors that might fail when you put things like dust covers on. So that's where we are with the monkeys. We have, because the light travel time from Saturn is so long, you know, we've got to basically plan everything ahead and then let the spacecraft fly and then see what happens. So the idea is that the very first landing is the biggest nail biter, but then after that we'll do a leapfrog strategy. So we'll fly over the area and come back and land, have a while to think about it. And then as we land at the next spot, we'll overfly the next one. So we just do that all the way from June to June to June until we get to the impact crater objective blanket and on up. But sure, we see other areas that look really interesting, definitely we'll diverge and go over and look at those regions in more detail. And we can also do, you know, more than the flight up and over again, we can do a jump and a hop, and we can, you know, do the same interdune area, but just nudge ourselves to a more interesting location as that way.
Yeah, thanks. Is it sort of, sorry, just one more quick follow-up and then it's all you. Is it like particle science? Like, will you get some sort of image down and you're like, this is what we're going to do, and oh, we have to bump there with the helicopter? Or is it like, is it sort of more like we land at a predetermined place and we do the science in the way that the instruments are oriented. I apologize, I know very little about Dragonfly other than it's really cool.
Well, I'm just thinking if I don't, I'm pretty sure we'll return images before we start doing anything, but I'm not 100, I mean, I think that's right. But I don't remember. We'll get images and then we'll say, yeah, should we drill? But also, you know, if you touch down on the surface of Titan, we drill and we get a sample. Then we get a sample, we get a handful of sand, we look at that, okay, to me, that's mission success.
Oh,
Because we don't, yeah, we just don't know anything about the surface.
yeah,
After that, to me, it's pretty.
yeah, the opportunistic science, is definitely something I, look forward to seeing, not just that, but future helicopter missions. Okay, I'm done.
I just wanted to add to your question about opportunistic science. Unlocking that, a big part of it is your compute on board, right? Having a cell phone chip on your helicopter that can do machine vision processing on board without having to send images back down to Earth. It sounds like there's a lot of perseverance folks in the room. There's still a Snapdragon on perseverance on the base station from Ingenuity, and maybe Burma has been working to use that for probably autonomous global planning. And I think there might be people interested in how to do image processing for signing up with the identification all on board. So if I could just throw a Snapdragon on everything that flies in the next 100 years, it's gonna benefit everybody.
And join that in our environment. I wanted to follow up on that thought. We've been playing with some mission concepts, thinking about where we could be going. And one of the challenges, right, we really love the opportunity of a discovery type of mission, not discovery class, but a drone can go see more potential science targets from the aerial, vector than the rover will in the same period of time, the same number of calls. The challenge, and Teddy caught the key point, we have a lot more compute. We don't have is a clear definition of what's interesting. And so if you can take 1,000 pictures a day, you can't upload even, 10 a day, depending on what your constraints are, you might not be able to upload every day. And so being able to put the decision-making about what's interesting for future follow-up on the helicopter requires knowing what's not interesting. And training model machine learning to identify everything that's not interesting so you can call down to not finding 100 things every day you want to go follow up on is easy for humans right now and hard for computers. And it's not a question of compute, it's a question of scientists being engaged in the development of algorithms to separate interesting from not interesting.
Yeah, I think, one thing to add from, Raven is, so we did have a science traceability matrix, and the team went in and had, before we started the mission implementation, they had specific ideas where to go on the plan. But interestingly, during the operations and the implementation in the field, they changed that. And they did a reconnaissance then science strategy, which I think was very interesting. So they used the helicopter to scout and then decide where to go.
That's the check for that. Was that something they went in deciding to do, or they started going to the places that they thought they wanted to go to, and then they realized, wait, we need to do some recon?
I'm not sure if I understood.
You said the science team had initially made some plans of where they wanted to go, but they ended up with a recon strategy first. Did they go into it knowing we want to do recon first, or was that something that they learned as they went to where they thought they wanted to go and then realized, wait, this is not the best?
Yes, I think it changed. So I wasn't on the ops team, so I'm not 100% sure, but so first of all, our landing site was a little bit off from where we initially planned to land. But the science operations team, I think had like 24 hours to change their plan. And I think one reason why they then changed the strategy, how they are going to do it, is to try to address all the science goals they initially wanted. And so once the data came down, they realized it wasn't feasible to go, or it wasn't likely that they were going to achieve the science goals. And so then they changed the plan and were using the reconnaissance flights and integrated that in the science planning. But again, I was on the implementation side of things, so that's primarily, but yeah.
Thanks. I was just trying to make sure I understood what the lesson learned was. All right, we are at 11:45. Anyone have a last burning question or comment? Otherwise, we'll switch to wrap up. This has been great. You know, time flies when you're having fun.
Something that was alluded to in the beginning, somebody mentioned that, they had been looking at either drilling or collecting samples with drones. So what sort of uses have you thought of? Because the drone is not very important. It's difficult to put pressure when drilling. It's the only way to do it. So you really just out.
Halo is drone is for, so you could get some, you know, good back pressure to push against. But that whole landscape is overprint now. So what sorts of things we need to drill. There's microspline rivers and UPLs. People have been looking at that for like the global payloads, for fall, and just stake this thing to some rocks with these microspines. Those weigh about 1 kilo. And you can imagine doing some sort of surface science with the helicopter back off. You could envision a drill, a very lightweight drill attached to chopper and find and just go directly down underneath. And again, you have 40 kilos to push against. But you're going to invest a lot in that. And you need the land or some other asset to here, like a Batman style utility. Someone will have to put attachments, you'll grab the drill something, drop off, and swap it out. It's been probably that happened.
I think, and just to follow up on that with because you're talking about drilling into like in situ rock and presumably or what have you. I think the beauty of active processes as well is maybe we can kind of just find a way, like, let's say you want to capture some volatiles expelled or something, kind of just fly on over there and let it happen. So I think that's I don't know, I don't know the specific technical jargon to describe that, or like dust in the air, for instance, getting that sample would be a lot easier than like having to insert an additional payload. So in the vein of the active processes theme, just one follow-up comment. And
yeah, so for Raven, we worked with 22 Robotics, and they had 3 different drones, all modified, or maybe 2 different drones, all modified Matrix 600. And we had a drone with a drill and a drone with different attachment, which is hook and a claw mechanism. And that was all for what recently happened. So actually, I think the idea was to test what best technologies are there to sample different materials. And so for the drill, I think we were able to drill into limestone. And the field, we ended up using a hand drill because it was always so hard. But then there's a paper coming out by Chen Chen, who is describing what different drills and also claws and scoops are useful for materials. Like if you have a loose rock, like a small rock, versus unconsolidated sediment, to find different samplers.
Excellent. Any other questions, comments on that long thread? Otherwise, I think talking about how we could use drone for samples is a pretty good note to end on. So thanks all for the great discussion today. I hope folks got some of what they were looking for through this. We have just about 10 or so minutes to wrap up, so what we're gonna talk about is moving forward, what people would like to see happen or suggest have happen. One of the things we'll come back to is thinking about for a future meeting, what the options are. Okay, so in terms of next steps, through this series, we have a focus issue within the Planetary Science Journal where we welcome papers, anything having to do with enabling planetary in situ measurements. In this case, it is focused more on the active processes, but we welcome review, science result, or concept papers. Main focus doesn't have to be on making actual in situ measurements, but if you have something where you can tie it to it. So for instance, my postdoc did some laboratory work and we talked about, based on the experience in the lab, what might that imply for collecting in situ observations of that type on other planets. So, and this is open for submissions, and we do have some TWISC funding left that can help pay for the publication costs. So contact me if that's of interest. And I think, and then I know we have some other really good papers that are coming out. So I didn't make a slide on this, but if people have good resources, papers, white papers that you want to direct this community to, I'll add that to our website. Currently, I have the 10th Mars abstracts, but I also have one other one that was sent in that was not 10th Mars. We can just keep adding to that resource list. So if people have papers that you want to help advertise, we'll add it there. And then we can also get it into the general Planetary in situ website at some point. Yes.
You had also mentioned to me that you can kind of cross concern. You had also mentioned an email that we can kind of cross list, because for instance, we're even submitting their special issue to PSJ, but you guys are going to submit a special issue to PSJ, and it's relatively easy for people to just have someone click a button and maybe, I don't know, Brian, you would know more, but if there's potential that you can just cross list your paper in both issues if you're already doing something.
Yeah, so a special issue on PSJ, all double-edged journals, but on PSJ especially, it's just a tag on the website since we're not printing these journals anymore. So
Yeah.
I don't know of anyone who's asked to submit to multiple special issues, but I don't see any reason why we couldn't just put tags to both special issues.
I will be.
There you go.
Awesome.
Yeah, so I wanted to advertise this this focus issue that we have. Welcome to submit to it. Tell your colleagues to submit to it. What I'm looking for, as I mentioned at the beginning, my metric, right, is that we eventually submit a lot of good, really compelling proposals to various space agencies or maybe commercial partners that are looking to enable these types of missions. So what we're looking for with this focus issue is collecting a bunch of references that would be really useful for people who are writing those instrument and mission concept proposals. And then beyond this, we are trying to generally continue growing this community. This is all mostly done in kind of our spare time, so it's been a little bit slow, but we do have a general website under the Planetary Institute umbrella. Drones is going to be a nice addition to that, and we do have a mailing list. So if anyone has interest in getting engaged with any of that, signing up for a mailing list, you're welcome to. I can put all this also on our website, the links, so you don't have to memorize it or type that all out. I think it's also in the abstract I had for 10th Mars, if you want to look at that one. Okay, so beyond that, I'm going to hand it then over to Brian.
Yeah. So an obvious next step also is that we just meet again to have some more conversation. As Serena has said, these workshops has often taken the form of just a tag, an add-on to an already scheduled workshop. But we also have done longer, exclusive focus workshops. So to sort of develop a sense for what folks' interests and availability is, I encourage you to visit that link, poll.ed.com, or you can use that QR code right there. And there's a poll that I put up to just suggest a couple of different possibilities for next year, workshops that are already scheduled to take place, and then some other options where we just set our own workshop. So maybe take 2 minutes, visit the website, let us know what you think, and then we can use that to decide what we want to do in the future. So examples of possible workshops we can tag on to, like maybe the AGU, that's a little bit late next year, but maybe that gives us a lot of time. Maybe we could do something around the LPSC, maybe around the DPS if you're planning to go to Finland. Or maybe we just do another exclusively focused workshop. I'd be perfectly happy with that too. So yeah.
In the top right corner of the QR code, there's a little download button. It's like making it.
There you go.
There we go.
Oh, sorry.
I just had to move mouse. Thanks.
For those interested in the building processes, there is a planetary use workshop next year and it will be starting here. So maybe that's
one of the options.
something to think about for this.
We know some of the science organizers, so that's definitely a possibility if there's enough interest.
Yeah, because there's no interest.
Well, and if our twist funding works out, then we also may have some travel ones for early career and senior students.
Well, right now, LPSC is the winner. So if you have any strong objections, alternatives. Let me see, I guess you just can't see the,
Give me the,
doesn't show you the results, does it? Is it working to show the results?
you want to share your screen? You're in there.
Oh, I suppose it's true. You might have to give me.
Do you not have a close vision?
There you go.
Okay.
Snap. And if you haven't, I think most people have, but if you haven't, please be sure to sign our list at the back. Give us your email address if you want to stay in touch with us for things. So right now it's looking like LPSC will be a good option. So maybe squeeze some other extra meetings.
Sure.
LPSC week.
Yeah, I think that was the list of what we wanted to accomplish today. So thank you all for attending. As Brian said, please do make sure that you signed in. Not only is this important for our record keeping, for putting in our report for this workshop and the funding that we got. But if you did not register, make sure your email address is on there. All of the recordings from today will be posted, and I'll send out an email to let folks know when that's happened, as well as see if you want to add, I can send all the other information that we've been getting. And I'm going to go into the back of the room once I close this out, and I will have the stickers and pins for attendees. So thanks all for coming. If anyone has feedback about how this went, please feel free to let me know. But let's keep the conversation going and get those drones to all these cool places. Thanks.